All right, welcome to Equilibrium, Chapter 15 review. Make sure you have a piece of paper and a pencil. Pause the video now to make sure that you can write down some notes here. If you want your note guide right here with the periodic table, that might be handy as well. Here's the reaction. A goes to B. Here's the reverse of the reaction. B goes to A. We can write the rate expression for this. Rate in the forward direction is equal to some constant K times the concentration of A, and we'll say it's to the first power. We'll say this is a single elementary step. Here is the rate expression for the reverse of the reaction. K, REV, meaning reverse, times the concentration of B to the first power. We'll say it also is a single elementary step. Equilibrium is defined as when the forward rate and the reverse rate are equal to each other. The forward rate and the reverse rate are equal to each other. So what we can do is say that rate is equal to rate, and K forward times A is equal to K reverse times B. K forward times A is equal to K reverse times B. These rate expressions are equal to each other. Solving for the K's, I'm going to divide both sides by KR, cancel those. Divide both sides by A, cancel both of those. I end up with K forward divided by K reverse is equal to the concentration of B, the normal product for the forward reaction, divided by A, the normal reactant for the reaction. Notice it's products divided by reactants. This is equal to something new. This something new is discovered in Chapter 15. It is called capital K, and sometimes it has an EQ down below it. This is called the equilibrium constant. These two constants come together to form the equilibrium constant, and it is always equal to the products to the power of the coefficients divided by the reactants to the power of their coefficients. This is called the equilibrium constant. If it's in terms of concentrations, we usually put a little C down below here. If it's in terms of pressures, we usually put a little P down below here. But as we've seen before, sometimes it's a mix of concentrations and pressures. Remember, for products and reactants, you can only put in aqueous things and gaseous things. You cannot put in pure solids, pure liquids, or precipitates. These things cannot fit in there because they don't have concentrations or pressures. Only things that are aqueous or gaseous go into the equilibrium constant expression. Okay? K can be a mix of pressures and aqueous concentrations. Not often, but we saw one in Chapter 20. Kp and Kc can be solved for from one another, though. So, for example, if you have an equilibrium constant written in terms of pressures and you want it instead written in terms of concentrations, you can use this equation. Kp is equal to Kc times RT to the delta N. This is given on the yellow periodic table right here. This equation right here is given to you in case you need it. It's underneath the equilibrium area where you find all your pH, your pKa, your Kw, Kb equations. Kp obviously stands for the equilibrium constant in terms of pressures. Kc stands for the equilibrium constant in terms of concentrations. R is 8.31 joules per mole Kelvin. T is the temperature in terms of Kelvin. And then N is the change in moles. So the moles of products minus the moles of reactants. And that's also given to you on the periodic table. So let's say that we had a equilibrium constant let's say that we had an equation 2a plus b goes to c, and it says that the equilibrium constant was 10. What would this tell us? Well, since it's 10, remembering that the equilibrium constant is products divided by reactants, it would mean that there's lots of products compared to reactants. Since the equilibrium constant is bigger than 1, we know that the products are favored. What happens if K was equal to 1 times 10 to the negative fifth? Well, since the equilibrium constant is equal to products divided by reactants, this would mean that the reactants must be large. The number must be 1 over some really big number right here. And so the reactants are favored and there's not much products. How about if K is equal to 1? Well, then the products numbers on the top and the bottom's reactants numbers, whatever they are, let's say they're 100, must be equal to each other. And so whatever the equation is for the top and the equation is for the bottom, they have to end up being the same for K equaling 1. So what happens if we have a reaction like this, where C goes to 2A plus B? And we know that the reaction up above, I'm just going to pick the first one here, is 2A plus B goes to C, and the equilibrium constant is 10. What happens if we have this reaction now? C goes to 2A plus B. See how these two are related to each other? See how they're related to each other? Well, they're the backwards of each other, right? When you reverse the reaction, do you simply reverse the sign of K? No, no, no. Remember, you always do the one mathematical operation that's more powerful than this one. And so it would be 1 over 10, or the inverse of 10. How about if I multiply the reaction? Now I've got this reaction right up here, but instead of 2A, it's 4A. And instead of B, it's 2B. And instead of C, it's 2C. Well, remember, I do the one mathematical operation that's more powerful than that. So instead of 10, it would be 10 to the second power. 10 to the second power. Okay? That's how it works when we reverse multiply it. And obviously, division would be raising to that fractional power as well. All right, let's say we've got a problem like this where I've got a reaction. They tell me the equilibrium constant. They tell me the initial values of hydrogen and oxygen in there. And then they tell me the equilibrium value of HI right here. This is a really popular question. As long as you can organize your data in the ICE table, then you're usually pretty successful, okay? You can see that since I've gained 1 over here and I started with none, I gained 1. And look at the stoichiometry, 2 to 1. For every 2 that I gain over here, I lose 1 over here. Since I only gained 1, I'll actually lose 1/2 over here. And since I lost 1 here, I would lose 0.5 over here. And so I would have ended up with 1.5, 1.5, and 1 over here. And I don't know if that ended up being K or not. I just made up a K. I didn't know for sure. But you can see how you can facilitate the ICE table by knowing something at the equilibrium value and then working backwards using the stoichiometry to figure out what it is. What's the ending concentration of H2? Well, I said it's 1.5 here because you did the subtraction. Get used to using those ICE tables and be a really good reader to find out what they're telling you in a particular reaction. So what if you're not at equilibrium? What if they tell you, here are some things, some concentrations. Where are you? Well, you can find this thing called Q. Q is the same thing as the equilibrium constant. Incidentally, the mathematics of the equilibrium constant is called the law of mass action, which is equal to the products to the power of its coefficients divided by the reactants to the power of its coefficients. The same thing you've already done. But Q is found when you're not at equilibrium. So for example, if I had certain numbers and Q ended up equaling 10, but I knew that K was equaling 1, the question would probably ask me, what do I have to do to achieve equilibrium? Well, remember that Q is equal to products divided by reactants. Same thing with K, products divided by reactants. And so what I always say to do when you're given these numbers is take the Q number and write it over 1, take the K number and write it over 1, and then ask, what would have to happen to the products to get them to look like K? What would have to happen to the products to get them to look like K? Well, it'd have to go from 10 to 1. So that means I'd have to get rid of some products and I'd have to go to the reactants to get to look to K. That's how you can always do those. Which way would it shift once I find Q to be able to know what it is at K? So take the number Q, write it over 1, take the number K, write it over 1, and then compare the tops. Compare the numerators and say what would have to happen to the numerator to make that happen. One big thing in chapter 15 that's introduced is something called Le Chatelier's principle. And Le Chatelier's principle says that a system at equilibrium, which we encounter a lot of, when it's put under stress, it will adjust to reduce that stress. Now, what things can you do to stress a chemical equilibrium? I'm going to go through a list. First of all, you could increase the concentration of a reactant or a product. When you do that, the reaction is going to push the other way to get rid of this extra concentration. So if you've got A going to B, if you increase the concentration of A, it's going to push it the other direction, and therefore it will increase the concentration of B. How about if you remove or decrease the concentration? Like, for example, say I decrease A right here by removing some of it. Well, then the reaction will shift left to replace some of that A. You don't change K's value, but what you do is you change the concentration ratio's amounts, keeping the ratio of products divided by reactants the same. Temperature does change K. And it's the one thing that does make a difference here. Temperature, when you change that, depends on the enthalpy of the reaction. And always treat temperature change like a product or a reactant. So for example, in this reaction, let's choose 2A goes to B, and let's say we have a delta H equaling negative 100 kilojoules. I would treat delta H as a product because it is an exothermic reaction and heat is given off. And so technically I should write this reaction as 2A goes to B plus heat. And I would write heat as a product. Now, I'm going to stress the system. I'm going to increase the temperature. Well, what am I doing? I'm increasing the heat. And I just said that if I increase the concentration of a product, I'm going to shove it to the left, and therefore I'll push the reaction towards the reactants. What if I decrease the heat? Well, if I decrease the temperature, well, then I'm removing some heat right here, and I'll shift the reaction to the right to replace that heat that's being taken away or being decreased because I'm decreasing the temperature. Do you see how you can use those? Remember these. These are super useful in chapters 16 and 17 as well. Lastly, how about if I change the pressure? Well, if I increase the pressure, I shift towards less moles of gas. If I decrease the pressure, I shift towards more moles of gas. So it's adjusting to reduce that stress. So if I've got 2A gases goes to B gases, and I increase the pressure of this equilibria right here, I should put 2 arrows there, I will shift towards less moles of the gas, so it should shift to the right. If I decrease the pressure, I should shift towards more moles of gas, and therefore I'll shift to the left and increase the amount of A. How about if I add a catalyst to a system? What does Le Chatelier's principle say should happen? Well, if you remember from chapter 14, a catalyst simply increases the rate of the reaction. It just makes it so I get to equilibrium faster. It will not change K, and it will not change equilibrium at all. No change at all to the equilibrium. All it'll do is get me to equilibrium faster. Well, let's look at a couple of released exam questions that use Le Chatelier's principle and use a few other of the K solving things. We'll back up to the very beginning. We'll start with the 2004 Form B exam, question number 1. And all these come from the question number 1 from those. All these chapter 15, 16, and 17 questions do. This first one says, for the reaction represented above, K sub P is equal to, and they love to give you a K and then tell you the temperature and tell you some stuff. Write the equilibrium expression. Well, it's products divided by reactants to the power of the coefficients. Notice how it's in terms of gases, and so he puts it, or they put it as P squared NH3, Pn2, P cubed H2. See how they put those as pressures or partial pressures of those, okay? I've also seen them written as NH3, and then they put a P right next to it like this, saying that it's pressures. Assume that the initial partial pressures of the gas are as follows. Now notice they say initial, not equilibrium. Calculate the value of Q, okay? It's plug and chug. Plug those values in, you end up with 0.166, all right? I plug those values in, nitrogen down here, hydrogen down here, and then NH3 right here. So Q, there we go. Predict the direction your reaction will proceed. Hey, we just did something like this. So they've got Q equal to 0.166. K is equal to 3.1 times 10 to the negative 4th. What did I say to do? Take and write it over 1. Now, what has to happen to Q to look like K? Well, this is obviously smaller, so this has got to get a lot smaller to look like K, which means I've got to reduce the amount of products I have therefore shifting it to the left, because remember, this is products divided by reactants. So reduce the amount of this to get it to look like this, which means I'm reducing my amount of products. So I should shift the reaction to, so the reaction must be, to shift the reaction to adjust to reduce that stress. Let's see, next one. Calculate the value of the equilibrium constant, Kc, given the value of Kp for the reaction is 700. So now we're going to use that equation that is on the periodic table. Kp equals Kc RT delta N. And N would be products minus reactants, so 2 minus 4, giving me a -2. Plugging the numbers in with a -2. Plug and chug, and I end up with 1 for K sub C. Really nice, easy little math problem there for plugging Kc and Kp. Next, they ask, the value for Kp for the reaction represented below is 8.3 times 10 to the -3rd. Here's the reaction. Calculate the value for this guy. So notice what happened between here and here. Notice what happened between here and here. You can see that I just took this reaction and reversed it. So what do I need to do with the equilibrium constant? One mathematical operation more powerful. Not just take the negative of it, but take the inverse of it. So take 1 over 8.3 times 10 to the -3rd, and I get 1.2 times 10 to the 2nd. Then they take this equation right here. Okay? And if I look at this equation right here, it is a combination. They say, what is the K for this? It is a combination of this reaction right up here at the top and a combination of the reaction on the page before. And I have to take those two reactions and multiply them together. This is a great question. So on the back side of this page, you can see here's the first reaction right up here with the K. I'm just going to rewrite that reaction and noting that the K is 3.1 times 10 to the -4th. Okay? So the other reaction was N2 plus 3H2 goes to 2NH3. 3.1 times 10 to the -4th. I hope I wrote that right. That's the K for that one. And then this reaction right up here was the NH3 plus H2S goes to NH4HS. And this one had 8.3 e to the -3. Now, how do I get it to look like this one in the box? Well, you'll see that this reaction should probably stay the same. And if I take this reaction and I reverse it to be NH4HS, double arrow goes to NH3 plus H2S, you'll notice when I reverse it and add these reactions together, oh, I'm sorry, I don't need to reverse that at all. My bad. What I was looking for to do was to take and have the NH3s cancel each other out, because you'll notice I've got 2 NH3 here, so I'm going to multiply this guy by 2, which means I have to take my equilibrium constant and square it. The NH3s then, when I add these two reactions together, would cancel out, and then I would end up with the 2H2S right here, the N2 and the 3H2 right here, and then I'd end up with the 2NH4HS right here. Now I have these two equilibrium constants, and normally when I do these things, people say, well, you added the reactions, so I should add these equilibrium constants. But remember, you got to do the one mathematical operation more powerful, so I need to multiply those two guys together, and then the answer turns out to be 2.1 times 10 to the -8th when I multiply those together. And you can see here's the number that I had and the number that I had right here. And there's the explanation for it as well. So that happened in 2004. You'll get something like that, I'm sure, somewhere in a question. Here's another partial question. This is question 1 from 2007. And in this one, they say, here's an equilibrium system. Here's Kp. when the system is at equilibrium, here's the partial pressure of Cl2. So that in an ice table, this is the E pressure. And then UOCl is this pressure right here. So this is the ice table of that. So calculate the partial pressure of O2, and here's the Kp expression. So you can write an ice table, fill in the Cl2, fill in the UO2Cl, and then this is a solid, so remember, don't put that in. And this one's the question mark. What's the ratio between these guys on this side of the reaction? You can always take things on the same side of the reaction and go ahead and relate them stoichiometrically in equilibrium, because some of this, of course, disappeared to create this. Well, this guy right here is 3 times as much as this. So I need to take this number, divide it by 3 to get that. So 1 mole of O2 for every 3 UO2Cl2. And so here's my equilibrium concentration of O. Now I know enough information here to take products, raise them to the power of their coefficients, divide them by reactants. So guess what they're going to ask me to find? Yep, the equilibrium constant. When I do that, 2.9 times 10 to the negative 13th. Then they go on and they combine some things from another chapter. Here's a flash to chapter 19. Calculate the Gibbs free energy. What equation takes G and relates it to K? Well, right here, negative RT natural log of K. Plug and chug, and you end up with 272 kilojoules per mole. On the back side, I think that's about it for that one. Let's look at one more. Here's 2008, question number 1. They give you a whole bunch of information in a little data table right here. And they tell you that solid carbon and carbon dioxide are placed in a rigid container. Notice right away there's a solid in there, not going to be in the equilibrium constant expression. Here's a gas and a gas. Write the equilibrium constant, products divided by reactants to the power of the coefficients. Calculate the number of moles. Here's a flashback to PervNert. Having you use some gas laws stuff in the very first question, even though it's equilibrium, they still want you to find the number of moles. Calculate the equilibrium for the reaction mixture at equilibrium, what the partial pressure of CO is. Calculate the partial pressure of CO. So here is a Dalton's law of partial pressures equation, a little more gas laws right here. Don't be shocked if this happens to you, because you know that question 1 is going to be equilibria, which is right here, but then they throw some gas laws stuff in there. Now they're going to have you use it. On the back side, they say, find the value of Kp. So they have you plug it in here for CO, plug it in here for CO2, and find Kp. Now this next question is great. A suitable solid catalyst were placed in the reaction vessel. Would the final total pressure of the gases at equilibrium be greater than, less than, or equal to the final total pressure of the gases at equilibrium without the catalyst? Justify your answer. How does a catalyst affect equilibrium? Does it shift it to the right, shift it to the left, or does it stay the same? Jump up and down, jump up and down. The total pressure of the gases at equilibrium with a catalyst present would be equal to the total of the pressure of the gases without a catalyst. In other words, the catalyst has no effect, Although the catalyst would cause the system to reach the same equilibrium more quickly, it would not affect the extent of the reaction, which is determined by the value of Kp. Once again, a catalyst has no effect on K. It just makes it get to K faster. In another experiment involving the same reaction, you've got a 2-liter container, 10 grams of carbon, plus some C and CO and CO2, partial pressures. Predict whether the partial pressures will decrease, increase, or remain the same as the system approaches equilibrium. Justify your prediction with a calculation. Bottom line, they want you to find Q, because they tell you the initial amounts here, okay? And they want to find out from those initial amounts what has to happen to become K. So it says the partial pressure is 2. Calculate Q. 2 squared divided by 2. You end up with 2. And then compare it to K. So I'd say write them over 1. Take them right over 1, okay? What does 2 have to do to get to look like 27? Well, it's got to get bigger, right? So you have to get more products, so it should shift to the right. Therefore, PCO2 should decrease as the system approaches equilibrium because it asks you what would happen to CO2. All right, there's a bunch of equilibrium constant problems. Please remember those Le Chatelier's principles because those come back to haunt you again in chapters 16, 17, 18, and 20. Being able to apply those can be super helpful in many other areas. Good luck on your equilibrium problem review.